In today's experiment, we're going to determine the molar mass of an unknown volatile liquid. And that's pretty amazing because when you determine the molar mass of an unknown, you're actually determining the size of the molecules. It's pretty amazing that that can be done in a really simple experiment. So we're going to be using the ideal gas law. And remember that for the ideal gas law, units are really important. If you use this value for R, you need to make sure that your units match with that so that they'll cancel. So pressure has to be in atmospheres, volume in liters, N of course is moles, and temperature in Kelvin. So you need to be able to convert back and forth between Celsius or from Celsius to Kelvin. And to get to Kelvin, you add 273.15. And to get to atmospheres, if you have millimeters of mercury, you're going to divide by 760. We treat the 760 as though it's exact. Usually it's not really, but we usually go, I think it has like 5 sig figs actually. But anyway, we treat it exact. However many sig figs you have in your millimeters of mercury, that will give you your sig figs for your atmospheres. I just find the word, just so that we're clear, vapor. Vapor is the same state of matter as gas. And so when we say vapor, it's just really meaning gas. A lot of times we use the word vapor for things that are normally liquid at room temperature, like we would say gasoline vapor, water vapor, and maybe we wouldn't say oxygen vapor, right? But anyway, so just know that that's the same state of matter. And then the word volatile is here because the unknowns that we give you are volatile liquids. They have to evaporate easily so we can get them into the gas phase to do the experiment. PV equals nRT only works for gases. So anyway, our unknowns will give you as liquids and we will vaporize them for the experiment. Okay, so how the experiment works is that we're going to put some unknown into a flask, and the flask will have a piece of foil on top with a little hole, and we will dunk it into boiling water for 10 minutes. And when we dunk it into boiling water, the unknown will vaporize and fill the flask. There'll be extra. So what'll happen is through this little hole, first, of course, will be air coming out, but then also some of the unknown will leave as well. So that this whole thing will just have the unknown vapor. So after it's been dunked in there for 10 minutes, the temperature of our unknown vapor will be the temperature of boiling water, and we're going to call that 100.0 degrees C. And of course, you're going to convert that to Kelvin. And then for the pressure of the gas that's in here is going to be the same as the pressure in the lab. Since it has this little hole up here, if the pressures aren't the same, gas would leave. So it will be the same as the room. So we'll say it's the barometric pressure. That's what we'll use. Okay, and then the mass of the condensate is the mass of the vapor is a little harder to get. If you have a flask full of this gas, this unknown vapor, and you put it on the balance, you're not going to be able to determine its mass. And there are lots of ways to explain that, but one way that's easy to understand is that when it's in the gas phase, its density is similar to its surroundings, and so you don't get the true mass of it. Just like if you took, you got on a scale and when you're in a swimming pool, since your density of your body is similar to the density of the water around you, you wouldn't get a true mass for yourself. So to get the true mass, what we do after we get the right number of molecules that are in there, after it leaves at this temperature and this pressure, then we're going to take those molecules and condense them by cooling it. And so once it cools, then you'll have a little bit of liquid down here. It'll be less than you had before, but that is your unknown condensate. So for the mass, we'll use the mass of the liquid, unknown liquid, condensate. Okay, now the volume, we need to get the volume. Well, the volume is a little bit tricky because even though our flask says 250 milliliters on it, that's not the true volume of the entire flask. Our unknown filled this entire flask, and we need to know the volume of the whole thing. It's not a volumetric flask or anything. So the way we get the volume is by using water. What we do is we fill it with water all the way to the top, and then we will weigh it, and we'll determine the mass of water. And from that we can use the density of water, and I'll do it to 3 sig figs. That's what we're going to use. And then from that we'll have the volume of water. And once we know the volume of the water, that is the volume of the unknown. Okay, and at that point, then you can plug in to the ideal gas law and get your answer. So let's look at an example calculation. Okay, a lot of given numbers here. First of all, when we start the experiment, you're putting 1.5 milliliters into a 250 milliliter flask. These numbers don't matter because we're giving you enough liquid that will fill the flask, but some of it leaves. The amount of unknown, that volume is not important, and neither is this. We just said that volume is not the true volume of the vapor. Okay, and then these other numbers are things that we can measure in the lab. So I didn't calculate any of those. Same with this one. This is measured in the lab. The two main data points you'll get are the mass once you have the condensate in there, and you'll have to subtract out the flask, and then also how much water fit in there, again subtracting out the mass of the flask. So let's just go through this in steps. So first we're going to do our volume, our pressure in atmospheres. So as we said, so this is from above. I told you the barometric pressure. And to get it to atmospheres, we divide by 760. And again, this millimeters of mercury has 4 sig figs. We treat the 760 exact, so our answer has 4 sig figs. Okay, our temperature in Kelvin. This is the temperature we're using. So we're going to add our 273, and I'm going to go ahead and round that off here. You could just leave the 1.5 and keep track of how many sig figs, but okay. And then what is the volume of the vapor? This is the trickier one. This is where you use water to find out. So what you do is you take the mass with the water in the flask. So it was 372 point. This is the flask plus the water. And then we'll subtract out the flask. And that will tell us the mass of the water. Oops. Let's do that again. Okay, we need another step here though, because that's the grams of water, and we need to know the volume of water that fit in there. So what we're going to do is use the density of water. The The density of water, we said, to 3 sig figs is 1 gram per milliliter. And so the thing to note when we do this is that we're going to lose sig figs. This has 6, but this density is not exact. It only has 3. So I'm going to go to 281 milliliters. Or you could keep track of extra digits there if you want to follow them. I'd probably keep them in my calculator. Okay, and so that's the volume of the vapor. The volume of the water equals the volume of the vapor. Oops. But we're going to need the volume in liters, so let's go ahead and convert that to liters. That's just like a simple conversion like that. So the key here on this one, the volume of the vapor is equal to the volume of the water that's in. That's the tricky one. Okay, mass of condensed vapor. Well, this one's pretty straightforward. We have the mass of it with the vapor or the liquid condensate. So this is the grams of the liquid, the unknown liquid, plus the flask. And again, subtract out the flask. Okay, and so 0. Okay, and this mass should be about a half a gram to 1.5 grams, something like that. Okay, next. Moles of condensed vapor. This is where we get to use the ideal gas law, and we should be ready to plug in. So this is where you use this, and we're making sure we put everything in the correct units. Okay, and then remembering our algebra, to get n by itself, I'm dividing both sides by all of this. And if I divide this side by all of that, I get should be a small number here. Let me change that word. Let's make that molecules to make it. Okay, I'll grab that in a second. Let's put this number up here. Okay, this business here, I said, is something kind of interesting because this is Avogadro's law. If we have the same volume at the same temperature and pressure, the number of molecules have to be the same. Equal volumes have equal numbers of particles. And it doesn't matter how big those molecules are, as long as we're in the ideal gas range where where those assumptions are valid. So that's kind of interesting, because if we all had the exact same volume for our flasks, since we're going to the same temperature and pressure, everyone would have the same exact number of molecules in their flasks. course, we won't all have the same volume of flask, because each flask has a little bit different mass and a little bit different volume. But anyway, so now we're ready to get the molar mass. And you're just going to use the definition of molar mass. It's grams over moles. So you plug in the grams of the condensate and divide by the number of moles you had. Oops. Okay. This number is and we determine that number above, and so I get 79.4 grams per mole, which seems like a normal molar mass, but what should you expect? I'm going to say in this range. A lot of the simple mistakes you might make doing this calculation will result in a molar mass that is way off. In other words, if you don't use the atmospheres and you use millimeters of mercury instead, it'll throw this number way off. This range, it's not just the range of our unknowns, but for something that's going to be a liquid at room temperature but be turning into a gas at 100 degrees C, that's about the size of molecules that might fit into that, because molecular size is involved in determining how much the molecules are attracted to each other, which determines what state of matter they're in. Anyway, that's what you need to know to do your calculations. Have fun.